So hello everyone, welcome to the Thermal Transport Cafe. My name is Mateo Zupancic from University of Ljubljana. I'm also happy to say that thanks to the organizers, this is already the fourth season of this online event. Our today's speaker is Assistant Professor Dr. Chiara Falsetti, who will present the work titled From Electronics to Future Aviation, Can We Bring Two-Phase Flows on Board? But before starting, let me provide a brief introduction. So Chiara Falsetti completed her PhD at EPFL, Switzerland, under the supervision of Professor Mirko Manini and co-supervision of Professor John Tome. Hope this is correct, Chiara. Focusing on flow boiling heat transfer and phase change phenomenon for on-chip cooling. Among other achievements, she was given the opportunity to be a guest scientist at the Experimental Thermal Hydraulics Group at Paul Scherrer Institute, PSI, to work on thermal radiation effects in nuclear reactor safety. And she also spent 6 months as a research intern at Nokia Bell Labs in New Jersey. She later joined Oxford as a postdoc, and relatively soon after that, she grabbed the opportunity at TU Delft to build her own research group. At Delft, she's currently an assistant professor following the academic career track. Her research interests cover heat transfer, multiphase flow, and thermal measurement techniques for the development of advanced and sustainable thermal management systems. The presentation given today will cover pool boiling heat transfer enhancement by surface modifications using dielectric refrigerants with low global warming potential as a working fluid. Various mechanical machining techniques like sandblasting and electrodischarge machining to tailor the boiling surfaces will be also presented. So we look forward to this presentation. Whenever you're ready, the stage is yours.
Thank you very much. First of all, thank you, Mateusz, for the nice introduction, and to Matthew and Professor Bucci to organize this very nice seminar event. I'm very glad today of being the invited speaker. So as Mateusz has already introduced, I'm going today to talk a bit about my research now at TU Delft in the Netherlands, that mainly focuses on cooling systems for sustainable aviation. Perfect. So I will start by introducing a little bit what two very different sectors, such as electronics and aviation, have in common. Then moving a little bit on aviation and what are the possibilities to make it more sustainable, and what we are researching now here at TU Delft. And then I will focus more on what I do here, so working on two-phase flow and trying to bring solutions that have been developed for the electronics cooling and data centers on board of future aircraft. This will essentially then, I will then conclude by showing you the pool boiling project that I carried out at Oxford University as a postdoc. So when we think about a data center and an aircraft, we tend to believe that these are two very different technologies, but in reality, they share some challenges. First of all, both these sectors are growing very quickly, and their demand is increasing, leading to an increase of power and energy consumptions. These also lead to an increase of environmental impact of both sectors, as I will show you. These two sectors also share some challenges that are more interested to our community, that are related to how to dissipate heat, possibly in a more and more sustainable fashion. So when we look and focus on data centers and ICT industry, we can see that the energy use is exploding. This is mainly driven by an increasing demand of internet traffic, cloud-based data computing, and storage and processes. Very similarly, the aviation sector is growing. In the plot, you can see the aviation demand is expected to grow by almost 3% per year. The three curves are essentially a high, central, and low forecast, but both are increasing in the forthcoming years. This has clearly an impact on our environment. So here on this plot, you can see the share of global CO2 emissions generated by different categories. And we can see that data centers and aviation are very similar in contributing to almost 2.5% of the global CO2 emissions. If we then focus on data centers, we can see that almost 40% of the energy consumed in a data center is related to cooling. So it's clear to see that if we can develop sustainable cooling systems, this might have an impact also, will have an impact also on the CO2 emissions. Aviation contributes almost 4% to global warming, also for non-CO2 effects, as vapor contrails and other pollutants. And we will see that this impact is essentially calling for disruptive technologies and a mix of solutions that are needed to cut emissions. And this is particularly challenging. And I will show you that thermal management and heat dissipation is crucial to develop a novel solution in the aviation sector. So let me see, I hope you can see the top page. Well, as I said, we need a mix of a solution to cut emissions, and more or less in the plot, we can see the share of this mix. First of all, we have to think, how do we design and fly planes? Meaning, how can the aerodynamics can improve, but also the routing and flight management can improve. This account more or less of 10%, if this is optimized, 10% of CO2 less emissions by 2050. Another big share, of course, the percentages are based a bit on the study. A big share is done by sustainable fuels. So this seems to be a promising solution to cut emissions. But another important part is related to new and emerging technologies related to novel propulsion systems. And among which I can talk about batteries. We can think about hydrogen or fuel cells based aircraft. And in all of these technologies, dissipating and possibly reusing heat is going to be one of the key challenges to solve. So looking at a bit into these promising propulsion systems, if we focus on batteries, so either for electric propulsion or for other systems on board related to the concept of more electric aircraft, we can see that there are still some challenges to solve. First, related to the energy capacity of the battery. This is still very low compared to current kerosene. But also another problem of batteries is related to their overheating that eventually brings them to failure. Looking at other solutions such as hydrogen and fuel cells, this can be thought either in a hybrid mode coupled with a traditional turbine or full electric, where the fuel cells can also essentially be a way to produce supply electricity to an electric motor. Here you can see in the picture two nice examples developed by Airbus for hydrogen and fuel cells. Well, also for these very promising solutions, there are challenges to be solved. Of course, this is related to the propulsion system itself. It's mass and obviously the storage problem of hydrogen. And in this, the heat exchangers component, so once again, the heat dissipation components are playing a crucial role. But also, if we think about fuel cell and fuel cell stacks, they tend to generate very high thermal loads that need to be dissipated on board. all these essentially very high heat fluxes have to be dissipated by traditional air-based cooling systems are not enough. So we will see that we need to think about something more efficient. So to recap a little bit on sustainable aviation, we saw that I show you quickly that all possible emerging technologies, including fuel cells, hydrogen, or batteries, will lead to higher and higher power on board and heat loads that need to be dissipated. It is estimated that the cooling needed will have to be on the order of megawatt, while currently is on the order of kilowatt. So the main questions behind my research here at TU Delft is, can we bring cooling technologies from data centers on board of future aircraft? There are many different cooling techniques, starting from the traditional one that is air and moving to liquid only cooling system. But today I'm going to describe two-phase cooling system, two phases intended as liquid and vapor phases. Here in the video, we can see an example of taken from Gigabyte of immersion cooling systems, where we are all probably familiar of this, where the motherboard is directly immersed into a pool of the electric refrigerant, and the liquid evaporates close to the hot spot, in this case the CPUs and the GPUs of the card. And thanks to the latent heat of evaporation, we can remove a very high heat loads. The advantage of, for example, this system is that is also completely passive, meaning that there is a passive recirculation of the refrigerant without the need of any pump or compressor. But I will show this a bit better later. We know that two-phase flow cooling, as I said, has the advantage of very high heat removal capacity thanks to the latent heat and a combination of latent heat and convection of the liquid. So it tends to be more efficient, and it allows to move and shrink the size of the cooling components. So it allows us to create very compact cooling systems, as the one you can see in this example from a recent article from Nature, where the micro evaporator in this case has the size even smaller than a coin. Although two-phase flow is very promising, it still have many open questions that need to be addressed before bringing it on board. And of course, some of the research questions that are open are linked to the heat transfer mechanisms of boiling, either pool boiling or flow boiling. In particular, what is the role of what is the role of the bubbles evaporation, and then the creation of a micro layer, and also in comparison to the rate, the heat removal rate that the liquid around the bubbles have. Another interesting research question that is still much research in the field is how can we optimize the surface such that the interaction between the two-phase and our engineered surface promotes bubble nucleations or enhance heat transfer. Of course, trying also to reduce the losses in the system, so pressure drops or even flow instabilities that can make the system fail. To try to answer to all of these questions, I now will present the pool boiling project that I carried out at the University of Oxford, at the Oxford Thermofluids Institute with Professor Ed Walsh. So this project was funded by Rolls-Royce, because essentially the interest was, again, to try to see if the two-phase flow, in particular immersion cooling, was feasible for aircraft. So the target was to dissipate heat from IGBTs, that are transistors, switchers that are typically found in high power electronics on board of aircraft. So we had a targeted dissipated power, and we had a very limited time to run this project, only 1 year. We also had to start selecting fluid and materials that are also compatible with aircraft platform. And in the end, there are also many questions related to the integration at the system level. So what are the boundary conditions on our aircraft, and can we integrate it in our current systems? So to do that, we developed we designed and then built a pool boiling facility. You can see it in the picture and in the schematic. It's a very simple facility. It consists of a pressure vessel that is closed by these nodes, and it has a pressure release valve and pressure transducer to monitor the pressure inside. This is the test section. I will describe it a bit better later. That is, as you can see, merged into the electric refrigerant, and the top plate here act as and the radiator act as a condenser. Essentially, the refrigerant evaporates, as we can see also on the schematic, evaporates near the boiling surface. And then the vapor goes up to the condenser side, where it returns back to a liquid state and by gravity returns down. So we have this passive recirculation inside the vessel. The condenser was the temperature of the top plate, so of the condenser, was regulated by a water loop. Again, pretty straightforward. And there were thermocouples in the liquid to measure the saturation, and also an auxiliary heater to maintain the liquid at desired conditions. The test section, you can see the schematic on top and a picture on the bottom, was made in copper with traditional machining. The dimensions are 20 millimeters of the boiling surface are 20 millimeters times 20 millimeters, and we installed 4 thermocouples along the vertical direction to measure the temperature of the copper and evaluate the heat flux going through our boiling surfaces. The copper is heated by flexible heaters that were simply mounted on the bottom side. In order to try to see if we could enhance critical heat flux and heat transfer. Critical heat flux is the limit after which the system can no longer operate because we have dry out conditions. We try to machine different surfaces on the boiling surface and investigate their effect on the boiling heat transfer. As you can see in the picture below, we machined with electro discharge machining, EDM, some microstructures. These are squared pillars with varying height and varying spacing. We choose sizes that were across around the order of the capillary length for the selected fluid, that is Novec. I will also present a slide later on this. And using microstructures, we were also interested to see if there were effects on the structure height and spacing on the boiling heat transfer. Similarly, we wanted to also investigate the effect of varying surface roughness of the boiling surface. So we adopted a different machining technique. We used sandblasting to essentially enhance the surface roughness of our boiling surface. So here you can see 4 images from the SEM that shows the 4 different surfaces corresponding to average surface roughness of 0.1 microns, 2.5, 6.1, and 9 microns. And this on the top right is a picture of the rough surface corresponding to 2.5. You can see already clearly the difference between this surface and the very smooth one. To select the fluid, we were giving temperature and pressure limitations from our industrial partner. For the temperature, we had to be between 300 Kelvin. Sorry, this is not degree C, it's Kelvin. So, and 300 and more or less 60 Kelvin. This is essentially driven by the temperature limit of the components that we wanted to cool. And the first step was to investigate just system running at ambient pressure, so not pressurized systems. For this reason, we decided to compare different fluids that are currently adopted in refrigerant and cooling systems by using as a, let's say, figure of merit, the critical heat flux correlation developed by Zuber. That essentially, as you can see in the equations above, is related to all the thermophysical properties of the fluid, liquid and vapor densities, surface tension and latent heat. And also depends a little bit by the liquid surface interaction by the constant C. So in the figure, we can see different fluids compared, again, comparing their nominal critical heat flux limit. And of course, there are huge differences, but in this plot, we don't see the operating pressure. So for example, for fluids as refrigerant as R134A, 245, and 1234ZE, these 3 curves, the critical heat flux is much higher than NOVEC, that is the pink curve, but they have to run at very higher, much higher pressures. Then, for example, methanol and ethanol had some flammability issues, as well as acetone. So we decided to, among different NOVEC refrigerants, we decided to go for a NOVEC 649 because it has a saturation temperature indicated by this dot of around 50 degrees, 49 degrees at ambient pressure. And it has a very low global warming potential, below 1. So that was also something that we had to consider. So now I'm going to show some heat transfer result of NOVEC 649 for the surfaces with different roughness. So now I'm comparing simply the sandblasted samples. And we can see that compared to the smooth sample, that is the blue curve, increasing roughness has clearly an impact on the boiling curve. First of all, the onset of boiling is anticipated to from around 20 degrees C of superheat to below 10. This means that our electronics can operate at lower temperature if we want to use a two-phase flow. And also the critical heat flux limit, that is the last point of these curves. So the limit of our operability increase of, I'm sorry that this is covering, but is around 18, the maximum is around 18 watt on centimeter square compared to 12 for the smooth surface. So we have an increase, already a huge increase with just by surface roughness modification. For this kind of fluid, I don't have now plots to show this, but we observe some degradation of the surface using this fluid, meaning that the surface roughness with time was essentially decreasing, meaning that our boiling curves would tend to shift again towards the right, so towards larger excess temperatures. And this is something that need to be further investigated. The effect of roughness is also visible on the heat transfer coefficient curves. So we can see that the transfer coefficient for a given heat flux, so for a given dissipated power, it increase of almost 4 times, simply increasing the surface roughness. Very similarly, we can analyze the boiling curves of the microstructures samples. So below you can see the different height and spacing that we tested. Of course, increasing the height or reducing the spacing has an effect on increasing the overall heat transfer area of the sample, and this is one of the main driving factors for which the heat transfer is improved. And we can essentially see that, again, we have the smooth sample as comparison. This is the blue curve. And we can see that all the microstructure samples outperform the smooth one. In particular, the best performances are showed for SM5, that corresponds to the samples with highest height. Again, these correspond to the highest area increase of surface heat transfer surface area. Another interesting thing that we wanted to investigate was trying to see if the effect of the machining itself on the surface had an impact on the boiling. So we also machine a sample without microstructures, but repeating the same surface finish of EDM, of electrodischarge machining. So this orange line with stars essentially is a sample without structures, but with a different roughness obtained by electrodischarge. And in fact, the roughness is enhanced compared to the smooth one of almost 20 times, showing an improvement of heat transfer. This improvement is also clearly observed also in the heat transfer coefficient that increases with the height of pins. But interestingly, if we look at SM2, SM6 and 7, that corresponds to the structure with different spacing, so same thickness and same height of the structures, but just different spacing between the arrays. We can see that in the end, this doesn't have a huge impact on the heat transfer coefficient, at least for the spacing tested, while the height has a much higher impact. Another interesting thing to notice on these results is that it seems that at heat fluxes closer to the critical heat flux, the heat transfer coefficient trend start to decrease. And this might be related to the formation of dry out patches, very large bubbles that start to merge, creating local spots where the vapor is in contact with the surface, and this might induce a degradation of heat transfer. So as I show you, we were able to, with two-phase flow, we were able to dissipate the targeted power. We observed improvements in the critical heat flux limit using either sandblasting to enhance the surface roughness. We observed almost a 2 times increase of the critical heat flux limit, and these went even up to 3 times when machining microstructures on the boiling surfaces. As a next step for this research, now there's a postdoc continuing my work. We would like to test different system pressure, trying to also change the subcooling. This should have, as we all know, should have an impact on the heat transfer and possibly also on the critical heat flux. And also try to develop some diagnostics to allow more fundamental studies, such as high-speed flow visualization and infrared thermography. So I hope I convinced you that it's very interesting to link 2 different sectors. This is essentially where the 2 sectors I worked on during my PhD, and then I moved, during my PhD I work on electronics cooling, and now I moved to aviation. And in my opinion, as researchers and as engineers, it's interesting to find these common challenges among very different applications, and try to influence and bring things from one sector to the other. So I think I concluded my presentation, and I'm very happy if there are questions. Very happy to answer.
Thank you very much for this nice work. And yeah, I'm opening the microphone for any questions. If there will be any put in chat, I will read them out if anyone is unable to speak now. Okay, maybe to start with something, I have a few questions, Chiara, and all of them are related basically to the fact that you mentioned possible deterioration of the fluids, which is then seen as a decrease in HTC, or let's say shifting the boiling curve toward higher superheats.
Yeah.
Do you think this is really related to fluid deterioration or maybe surface oxidation? So did you perform any XPS analysis or at least EDS Raman spectroscopy to detect the mechanism?
Yeah, thank you, Mateusz, for the questions. I must say that for the time being, we haven't run a specific test to investigate this degradation. After we found these results, we were repeating test multiple times, and after seeing these results, we decided to move to the microstructures. As I explained, we had a very short time, but that is absolutely something that needs to be investigated, and either it can be either related to the chemical composition of the refrigerant. I heard that this fluid will be also dismissed. It attacks surfaces apparently, and but definitely there might be other mechanisms, but no, we haven't investigated that further.
Yes, thank you. Many fluids are in fact thermally or photolytically unstable, deteriorate over time, and 3M is actually removing some of them, and it's a very interesting question. Yeah, indeed. Okay, so next question, the mic to Adia, please.
Hey, thank you for the great talk. I have a few questions just to understand well. So when you say that you used a reference surface, the SR1, how was the reference surface chosen? Like, did you do some polishing techniques, or and how was, like, did you do AFM to see that it was super smooth, or yeah?
So I haven't, thank you for the question. In fact, I haven't specified that. The SR1 is essentially the one I'm showing here on the top.
Yeah.
This copper block was a CNC machined, and then we asked the manufacturer to polish the surface. And then all the samples were characterized in our material department with an optical profiler to measure the roughness. And also, as you can see in these images, we did some SEM scan electron microscopy to also investigate the structure. And for the, I don't have a picture here, sorry. And for the microstructures, we wanted to measure the uncertainty of the machining. So we also evaluated the uncertainty on the geometry.
Okay. How repeatable is sandblasting procedure? So when we make 2.5 micron, 6.1, I'm not sure how reproducible this is if we want to make it again.
Yeah, that's also a very good question. In our case, the sandblasting was performed with a machine.
Okay.
We had produced, for this reason, we had sandblasted every time 10 samples on a flat surface of the same material, and we're characterizing them. And I can say that the roughness was changing. For example, a roughness of 2.5 was changing of 0.1, 0.2 maximum between samples.
Okay.
So I would say is quite repeatable. The problem, again, related to the roughness for sandblasting is that we noticed a degradation. So after time, we were measuring again the surface roughness, and we observed a reduction after time in contact with the fluid.
Even if it was water being boiled, would you still see the difference, or was it?
So we haven't worked with water. In my memory, in the literature of water pool boiling, I don't remember such a degradation for sandblasted samples, but maybe Mateusz has worked with water and can say more. I don't want to ask a question to my.
Yeah, I would rather hand over the microphone to Piero Colonna, please.
Yeah.
Hi, Chiara.
Hi, Piero.
I have a curiosity, actually. You know that I'm not very knowledgeable on these things. Have you run an uncertainty analysis on your measurement? What is the uncertainty bands I can expect on those charts?
Yes, so of course, yeah, we had to run uncertainty analysis. Of course, the uncertainties can go up from the propagation of error. So for the heat transfer coefficient, we had a maximum uncertainty of 10 to 12% maximum, depending on also the conditions, because these varies with temperature and power. On the critical heat flux, so on the Q, on the limits, we had a maximum uncertainty of around 4 to 5%. Meaning that for the maximum, for the most performing structure is around 1 watt on centimeter square, right? Yeah, more or less.
And the temperatures? How well can you set them?
Yeah, so the temperatures are measured with the thermocouples, and we calibrated them. We didn't use the manufacturer calibration, but we calibrated them in situ in a water bath. So the uncertainty on the temperatures goes down to 0.1 degrees.
Thank you very much.
Thank you, Piero.
Okay, Zhengmao, please, it's your turn.
Hi, Chiara. Thank you for your talk. And I have a probably not so technical question. As you mentioned, the parallel between the data center cooling, electronics cooling, and the aviation thing, I was wondering, is there anything like more specific to aviation, for example, I can imagine the orientation, acceleration may change things, and would be like happy to learn your thoughts on it.
Yes, yes. Thank you for the question, and that's absolutely true. So it depends a lot on the final applications in the aviation sector, but of course, just the inclination when taking off and landing change. In fact, we ran some modeling on that. And it's interesting to see that if the angles are still limited, the electronics can still be partially merged, so it's still better than air cooling. But if we move to different type of aircraft with different flight mode, then immersion cooling has to be again reevaluated, because if the operations are below a few seconds, it's still okay, because the electronics can operate few seconds without the fluid, but that would be an extra step. In relation to this, there is a very nice study that has been carried out by a larger consortium of European university with the European Space Agency, where they studied pool boiling on a space station. So in that case, there are even effects of different gravity conditions. To address that, they investigated different surface types to try to push bubbles, leaving the surface even when gravity is not helping.
Okay, thank you. I think this is a good answer to that. So Suhas has the next question. You can open your mic. Yeah.
Hello, Dr. Falsetti. Thank you for the nice talk. My question is actually related to the previous one. If immersion cooling is what is needed for avionics, would you say there's an effect? I'm assuming that this entire setup is going to be confined in a small space, but is there an effect of how much liquid is there above the heater surface? And is that of interest to you as a research problem?
Yeah, thank you for the question. So from this question can be answered both from a application perspective and from a fundamental perspective. So there are studies who investigated the effect of the height of the liquid column on the surface. It seems that has an effect on the liquid possible recirculations, and also eventually an effect on the pressure, the change in pressure in the liquid column. From the fundamental part. From the applied part, the liquid quantity essentially drives the weight of the system. So in that case, of course, for an aircraft platform, the weight is very critical. So this is why we were trying to keep the liquid column as short as possible to also account for that.
Thank you.
If this is a reply to your question.
Yeah, I was basically just wondering if it is going to be confined in a space. Essentially, pool boiling relies on removal of vapor very effectively. If it is going to be confined in a space, how would you expect a practical implementation of this? And would there be practical limitations in terms of the liquid height itself?
Yes, there will be practical limitations of the liquid, again, related to the size and the compactness and the weight of the system, but also on the boundary conditions, meaning the temperature at which the system is installed. So in our lab, there's an ambient temperature, and we can control the condenser side, so the top plate, very easily. But what happens if the external condition varies, and maybe can we integrate it in a system where we can maybe exploit colder temperatures outside or close to the skin of the aircraft. So these are all open questions that are absolutely very interesting and still need to be investigated by my group.
Got it. Thank you.
You're welcome.
Okay, thank you, Said. Next question, and then we have one from the chat as well.
Thank you for the very interesting work that you are doing. My question is along the same line of Suhas's. When it comes to basically airborne platforms, orientation is significant effect. And is pool boiling acceptable? I mean, I can only imagine being able to have flow boiling. Otherwise, basically, it would be a failure point if we implement any pool of two-phase that is susceptible to change in performance due to orientation.
Yes, the orientation is indeed one of the main challenges to then integrate system integration. So definitely flow boiling would solve a bit the problem of orientation or capillary flows if either using, again, capillary forces or a pump or a compressor to drive flow. In case of pool boiling, again, this is really related to the type of applications because the orientations are usually more or less known for civil aircraft. So one could eventually study a system that guarantees full immersion or partial immersion during the whole duration of the flight and of the mission eventually. So I think there are challenges, but now that what we are seeing in this picture is the vertical traditional type, but we can also think about moving the electronics and packing the electronics in such a way that is all the time merged or partially merged.
Thank you.
You're welcome.
Okay, thank you. I'll read the question. There are three questions actually, but quite related. So let's have all three together. So Rodrigo is asking, how do you plan on adapting the high-speed video in the current section, or maybe planning to design a new one? And what kind of views are you thinking of? Side view, top view, and bottom view to observe the bubbles? And are you thinking also of changing the copper heater to some other materials?
Yeah, thank you for the questions. So the current setup is in Oxford, and I'm in Delft. So this won't be in a way my decisions for the future, but there are discussions on high-speed visualization. So first of all, as we can see, this is a cylindrical vessel. It is not particularly good when then using a flow visualization. So there are some design already design studies started to eventually create a vessel with flat surfaces to allow flow visualization, because this is not very easy. This was done to test higher pressures, so it has to be a circular, a cylinder geometry. In terms of materials, we started with copper because it's again very commonly used. In reality, the next phase of the project will be directly to merge few IGBTs that are provided by the company. So the project is expected to move towards higher TRL. So the idea is to develop a small facility to create flow visualization, possibly with flat plate, but on the other hand, move to higher TRL. So test directly with a transistor rather than a copper or aluminum samples.
Thank you for this answer. I don't see currently a question, so I just have one. I'm thinking of one particular thing, which is maybe even giving me some nightmares lately. You can see that the enhancement that you get on, let's say, relatively simple surfaces, sandblasted surfaces, on the level that we have on some advanced laser created periodic surface structures also for the electric fluids. So I'm thinking basically anything you do, as long as the land scale of these microstructures is small enough, is good enough, and it has the same level of enhancement, plus minus few percent. And thinking of that, what's even there for us, right, to develop such an advanced surfaces? In some cases, you can really go simple and have an enhancement on the same level as anything else. What do you think about it? I mean, have you checked the literature lately, or did you review how do other surfaces perform?
Yes, so as we know, the literature on surface enhancement or engineered surfaces on pool boiling is becoming very, very vast. I would say that I found very interesting studies that are changing the wettability of the surface locally to, in a way, create a pattern on the boiling surface to even create different pathways for the liquid for the cold liquid to come closer to the surface and bubbles to leave, creating actually different columns of liquid and vapor leaving and reaching the surface. Those are very interesting. There are many studies on chemical coatings produced by many different techniques. In my opinion, if you want this system to be finally used in real applications, we also need to think about what is cost effective and what is repeatable and easy to machine. So I would say that on the fundamental research, everything is very interesting. Then when we have to think about proper applications, Mateusz, to reply to your point, we should probably narrow it down to what is the simplest and most, in the end, cost-effective solutions to generate an enhancement. And this goes along also a lot with the materials and applications, because sometimes you can't laser machining a CPU, or maybe yes, but then, you know, this has to be tailored to the application, I think, too.
Yeah, I fully agree. Yeah, that's a very good perspective that needs to be taken into account in the future. So since there is no more questions and the 60 minutes mark is approaching, I would like to thank our today's speaker again.